Today I'm going to be talking about a technique that can be used to determine the relative proportions of different sources of sediments in streams, known as sediment fingerprinting. According to the United States Environmental Protection Agency, suspended fine sediments are the leading cause of surface water impairments in the United States. And there are numerous sources of suspended sediments in streams, in rivers, in lakes, and reservoirs, which can be categorized into two main classes. The first of which is an increase in sediment supply to streams. This is largely caused by changes in land cover usage. For example, removing natural vegetation from the landscape to make room for agriculture or grazing lands can destabilize topsoils, making them more likely to erode and cause sedimentation in streams. The second category is activities that cause an increase in the transport capacity of sediments within streams, largely related to changes in the flow rate or the carrying capacity of a stream to hold and move sediments downstream. There are also numerous consequences of increased sediment contamination in streams, ranging from, but not limited to, decreased water quality, impaired habitat, decreased biodiversity, as well as increased burden on water treatment plants, all of which have their own associated costs, whether it's the cost of treating drinking water or reduction in ecological services and functions. Now, there are numerous management practices for dealing with sediment contamination. The first of which relates to reducing the upland loading of sediments to streams, or cutting off sediment at its source, which is ideal. And this can be done with responsible land use. For example, responsible agricultural practices, such as certain tillage practices that decrease the amount of topsoil disturbance, can be used, as well as vegetation cover, which provides root stability and coverage from the elements, which can decrease soil erosion and thus sediment burden to a stream. On a much smaller scale, within its particular reach, you can reduce in-stream transport using dams, sediment traps, or turbidity curtains, which can be seen in the bottom left. However, in order to accurately and efficiently implement any one of these techniques, it's important to know what your main sources of sediments are, which is where this technique, sediment fingerprinting, becomes useful. Sediment fingerprinting is a technique that identifies suspended sediment sources in a watershed and can then allocate the amount of sediment from each one of these sources, so it is then easy to identify where restoration activities should be focused. Now, these techniques leverage a combination of natural tracer technology, field data collection, laboratory analysis of sediment characteristics, both physical and chemical, as well as statistical modeling techniques. Now, there are 5 main steps that can be used to do sediment fingerprinting, which I will go into depth on each one of these. First is classify your sediment source. So where is your sediment in the watershed originating from? Number 2, identify unique tracers. So what physical or chemical attributes can you use to determine where sediment in a stream is coming from? Third is represent your sources and your sinks. What are the chemical characteristics of each one of your unique sources, as well as the region where they all mix in a stream? Fourth is to account for tracer fate. And lastly, once you have all this information, you can run a model to determine sources and relative contributions of each source to sediment in a stream. So the first step, source identification. Depending on the scale of your watershed or your resources, you might use a variety of different techniques. For example, interviewing stakeholders, landowners, government agencies who know the history of the watershed might be useful in indicating where sources of sedimentation arise from. You can also do field inspections where you walk the banks of the streams and look for direct sources of sediment that way. However, if you're dealing with a much larger watershed, that might not be possible, in which case you can implement the use of aerial photography and remote sensing to identify erosion scars or other possible sources of sediment. Lastly, soil surveys can be done, which you can see on the bottom left, for example, where you identify the spatial distribution of different soil types to identify which regions might be the most prone to erosion. Once you've identified potential sources, the next step is to identify which tracers you're going to use. Now, tracers can fall into two main categories, physical or biogeochemical. Some examples of physical tracers include sediment particle shape or size distribution or color. Now, biogeochemical tracers can be split into three further categories: organic, including organic carbon, organic nitrogen, their stable isotope signature or the ratio; inorganic, including a variety of minerals or metals, iron, manganese, aluminum, copper, to name a few; as well as radionuclides, such as cesium-137, which is commonly used. Now, these often are derived from radioactive fallout and have a certain half-life, and then can thus be used to detect very small concentrations in the environment. Once you've identified your tracers, a variety of statistical methods can be used for optimization, which I will discuss later. Now, once your tracers are identified, the next step is to characterize your sources as well as your mixing site. So, in this diagram of a hypothetical watershed, we have three separate sources: forest, agriculture, and urban. Now, in order to correctly use this fingerprinting technology, you need to measure the concentration or the characteristic of your tracers at each one of your sources. So at your forest site, your agricultural site, and your urban site, as well as downstream confluence where all three of these mix. So you have a characteristic of your end member site where they mix, as well as your three sources. Now, depending on the tracer that you use, you might need to account for their fate. And what this means is that as particles and elements are transported downstream, they might transform or decay. For example, physical changes might include fractionation, aggregation, or disaggregation, all of which can change the size distribution as sediments are transported downstream. So, for example, if you were to use particle size or size distribution as your tracer, you would need to account for any of these changes that may be taking place. With regards to biogeochemical changes, dissolution of minerals, as well as decay of radioactive material and organics might need to be considered. For example, many nutrients are taken up by biota and thus behave non-conservatively. So if you don't account for that, you might have an inaccurate prediction of source allocation of your sediments in the watershed. Now, once the first four steps are complete, you've identified potential sources, you have chosen appropriate tracers, you've characterized your sources and your mixing site, and you've accounted for any potential transformations of your tracers. The last step is to run a model. Now, there are numerous statistical models that can be used, each of which varies in complexity. There's pros and cons to each one, but for the most part, they're all based on a very simple mass balance equation. So to illustrate this, I have a very simple two-source model. You have source 1, source 2. They mix together at your mixing site and cause your mixing solution. Now, there are a couple basic properties of these mixing models. The first indicates that the concentration of sediments at your mixing site is equal to the sum of your sources. So 1 plus 2 equals your m, which you can see right here. The next is that the characteristic of sediment at your mixing site is related to both the quantity and the characteristic of your sources. So in this case, source 1 is blue, source 2 is yellow, and if you remember back to your elementary art classes, you know that blue and yellow mix together to make green. But the quantity of green, as well as the shade of green, is related to the quantity of blue and the shade of blue, as well as the quantity of yellow and the shade of yellow. So once you know these certain characteristics, that is the quantity and the characteristic of your end member as well as your sources, through some relatively simple math, you can determine the relative fraction of sediment coming from each individual source. Now, to illustrate this in a real-life context, I'm going to examine a case study where a watershed in northern Georgia was analyzed using sediment fingerprinting to determine the sources of sediment in the southern Piedmont stream. Now you can see the watershed of the North Fork Broad River over on the right, located in northern Georgia, and what you can see is that it is a relatively altered watershed. There are multiple flood control dams throughout the entire watershed, as well as a channelized portion towards the southern part. Now, in these southern Piedmont streams, there's been a long history of sediment pollution, which has resulted in degraded water quality, decreased habitat, decreased macroinvertebrate community health. However, in a lot of these watersheds, they're not sure where the source is coming from, whether it's upland agriculture or is it legacy sediments coming from bank erosion. So in this study, they decided to answer this question. They were going to use sediment fingerprinting. And based on land cover, they identified several sources of potential sediment. Surface soils consisting of cropland, pasture, and forest, and subsurface soils including stream banks, unpaved roads, and construction sites. Now, in this case, they analyzed a broad range of different tracers. Particularly 21 potential tracers were all analyzed. And this was done using a stepwise discriminant analysis, which is essentially a statistical process in which multiple tracers are added together to determine the cumulative rate at which they can accurately categorize where sediment is coming from. And in this particular study, 2 tracers were selected, namely cesium-137 and stable nitrogen isotope N15. Next, looking at sources and sinks, suspended sediments, which are your sinks, those signatures, in this case, plot within the source. So to explain this, the first graph we have here on the right, we have cesium-137 on the x-axis and our stable nitrogen isotope signature on the y-axis. Now, the vertices of this triangle represent your sources. So we have bank, construction or paved roads, and pasture. And as you can see, all of the open triangles represent the signature of suspended sediments in the mixing zone. So in this case, cesium and stable nitrogen isotopes are a good fit because all of your suspended sediment signatures fall within this characteristic triangle. Now conversely, it was found that chromium is a non-conservative tracer. It's not a good tracer in the system. That's because, as you can clearly see, the signature of suspended sediments falls outside of this characteristic triangle. Now, the final step is to model. In this case, a load-weighted model was used, which took not only the sediment characteristics from each source into consideration, but also the loading from each source to determine the relative sediment contribution in this stream. And as you can see on this triangle diagram here, the majority of sediment in the stream was determined to come from bank erosion, about 60%. And you can see, starting at about 40% to almost 100% of that signature was attributed to bank erosion. The second most abundant source came from construction and unpaved roads. You can see this falls roughly between 40 and about 80%. The average was about 27. And pastures made up only about 13%, much less than the other 2 sources. So to conclude, sediment fingerprinting uses unique tracers to identify suspended sediment sources in streams. Further, it uses statistical models to determine the contribution of each one of these sediment sources to suspended sediments in streams. And there are management implications for this study. Namely, there's limited funds for restoration projects. As such, we need to prioritize where we're spending our money so we can get the most bang for our buck. We can be the most efficient with the money that we have. In this case, sediment fingerprinting can be used to identify dominant sources of sediment pollution so those funds can be focused on the most crucial areas that are in need of restoration. And ultimately, this helps prioritize restoration projects, making the whole restoration project go more efficiently, more smoothly, and we can make better use of the limited funds that we have available.